Yeah, so it's my pleasure to introduce Craig Connolly. Craig has been a postdoc with me for about the last year, working on a data integration and I'll call it upscaling project to understand the geographic variability of arsenic contamination and how that's related to its underlying geology. Craig comes to us from the University of Texas. Craig comes to us from the University of Texas, where he studied marine science, actually looking at the role of rivers and terrestrial cycling in carbon and what was exported to the Arctic Ocean and controlled the chemistry of the Arctic Ocean. And before that was a student at Holy Cross and is originally a Hudson River native in the region. His perspective, being different from arsenic, has been much appreciated, and we look forward to hearing more about his statistical and sort of informed statistical approaches, I guess I should say, in remote sensing at predicting arsenic concentrations in Cambodia.
I'm gonna share my screen. Okay. So you guys see the presentation? Okay. So yeah, before starting, I'd just like to acknowledge that in addition to a part of our collective SRP research effort, as Ben mentioned, this work is part of a USGS PAL group project led by myself, Mason, and Beck from Union College, as well as Athena and Ben from Lamont Doherty at Columbia. So the title of my talk today is Linking Flooding to Groundwater Arsenic Heterogeneity and Risk of Exposure Across Scales in Southeast Asia. So chronic exposure to high levels of geogenic arsenic or natural arsenic afflicts more than 200 million people worldwide and over 100 million people living on floodplains of South and Southeast Asia alone. The most common form of arsenic exposure is through the ingestion of groundwater. And the excessive consumption of this arsenic-contaminated groundwater is associated with a wide range of illnesses, including skin disorders, heart disease, cancers, diabetes, and cognitive impairment in children. Now, one of the reasons why it is very challenging to understand the causes of arsenic contamination in groundwater is because its distribution varies by orders of magnitude over very small spatial scales. For instance, you can find sharp contrasts in arsenic concentrations from, say, safe drinking levels less than 10 micrograms per liter to extraordinarily dangerous levels beyond 500 micrograms per liter in groundwater wells that are only a few hundred meters away from each other. So it's this small scale variability that makes it remarkably difficult to identify the principal environmental conditions that regulate arsenic levels in groundwater and explain this extreme heterogeneity. And therefore, it makes it difficult to assess the risks of exposure at fine scales that are the most relevant for making management decisions to reduce these levels of exposure. Now, to solve this problem, thousands of scientific studies have sought to address the environmental conditions that regulate arsenic contamination. And to briefly summarize, what these studies have shown us is that arsenic, which is naturally contained in sediments, such as iron oxides, to be more specific, they are released, the arsenic is released in wet and anoxic environments when there's enough organic material present to drive microbial processing. These environments typically exhibit strong reducing geochemical conditions, which favor the release or dissolution of this arsenic from these sediments. Now, this now mobile arsenic is now free to be carried by groundwater laterally or vertically throughout an aquifer. Now, the importance of these environmental conditions, as well as the interaction with other relevant processes, they vary markedly between aquifer systems that differ in their geology and their geomorphic setting, as well as their hydrologic connectivity to surface water. So their relationship to surface water is important. And now to kind of provide an example, but also to kind of show you the schematic and illustrate the mechanisms that lead to arsenic contamination, I want to walk through a real scenario from Van Phuc in Hanoi region of northern Vietnam, near the Red River Delta. So this area in Van Phuc hugs the Red River, where its ground is composed of a layer of young and organic rich sediments that were derived from the river. They are often covered and intermingled with ponds. And then deeper into the ground, there is a shift going from young sediments, typically containing high arsenic, to much older sediments containing low arsenic as you move from the river more inland towards Hanoi. Okay. So regions closer to the river that receive a lot of sediment from the river typically contain the highest amounts of sediment-bound arsenic. Now in this example, the main source of groundwater recharge is from the Red River, although it can be from other forms of surface water and especially in other areas too. As this groundwater moves through this young arsenic-rich sediment, it also receives inputs of organic matter, say from a pond or from the shallow surface horizons, which then combine with these arsenic-rich sediments in very water-saturated wet conditions. And it leads to, or sets the stage for arsenic mobilization into the groundwater. Now this groundwater can potentially stay put for long periods of time, accumulating more arsenic, or it can migrate into adjacent aquifers that can be contaminated or uncontaminated already. Now, depending on the geologic and the chemical setting, this can be a good thing or it can be a bad thing for contamination. And in this case, as arsenic contaminated groundwater moves from the younger aquifer to the older aquifer, there's a subsequent shift in geochemical conditions, which actually causes the aqueous or dissolved arsenic in the water to be removed from solution and then put back into the solid phase, effectively filtering it from the groundwater. And so the result is that groundwater is safest further from the river near Hanoi in these kind of deeper, very old aquifers. Now, these gradients in arsenic that can go from safe to very dangerous contaminated conditions, they vary across several kilometers. But depending on where you live in relation to sharp contrasts in these environmental conditions, arsenic can also vary dramatically within only a few hundred meters. So using improved understanding of these conditions that are responsible for groundwater arsenic contamination, scientists have more recently looked to develop statistical models that incorporate relevant geospatial information and machine learning techniques in order to explain and predict and scale the groundwater arsenic heterogeneity. However, many of these models yield aerial averaged probabilities of exceedance. So for instance, the probability that arsenic in the groundwater is going to be above 10 or above 50, rather than explicit arsenic concentrations. And some of these models often, they require measurements of groundwater composition. So actually measurements of the chemicals in the groundwater. And so thus they're typically unable to capture this small scale variability in the actual concentrations of groundwater that is most relevant for making these public health decisions within communities. Now these limitations are particularly significant in South and Southeast Asia, where available geochemical and geospatial data sets are often limited, and those that are available are quite coarse. So for instance, a map might be greater than 1 kilometer in scale. So to overcome this challenge requires environmental predictor variables that are more mechanistically tied to the controls of arsenic mobilization and groundwater contamination. And that can be acquired remotely at a very fine spatial resolution that matches the scale of the observed arsenic heterogeneity in nature. And flooding is one of these potential key variables, which can be collected remotely via satellites at a very small scale, about 30 meters. Studies have demonstrated recently that flooding plays a clear role in saturating sediments with water and initiating these anoxic conditions that are needed for arsenic release. Moreover, floodwaters heterogeneously deposit massive amounts of sediment across the floodplain, especially during the monsoon season, which provides a very necessary source of organic matter and reactive arsenic-bearing iron oxides or sediments that favor arsenic mobilization. So following this train of thought, we hypothesized that the duration and frequency of flooding, along with other relevant geomorphic conditions, control the water status and the chemical gradients in the near surface sediment horizon environment, which in turn regulates arsenic mobilization and toxicity in groundwater and can help explain this extreme spatial heterogeneity. So in this study, we set out to investigate the role of flooding and leverage a high resolution and mechanistically defendable predictor variables that are related to flooding and other environmental features to both explain and predict the groundwater arsenic distributions and levels of exposure. So building from this hypothesis, we first developed a conceptual model that describes the relationship between flooding behavior and groundwater arsenic contamination. And to briefly summarize, we outlined various hydrologic regime scenarios that we expect align with the degree that flooding regulates arsenic mobility and groundwater contamination. So for instance, we expect that safe arsenic levels to originate from recharge environments that are dry or typically don't flood, as well as those that may flood frequently during the monsoon season, but comparatively they don't flood for a very long duration. So maybe it's a kind of flashy event that then dries out very quickly. On the other hand, we expect dangerous levels of arsenic to originate from areas that experience much higher degrees of flooding duration and frequency, and then expect both safe and unsafe arsenic levels to result from areas that experience unusually high degrees of flooding. So kind of up in this portion of the graph. And those might, have some kind of strong association with permanent water that might lead to those kind of abnormally high levels of flooding. So then we set out to acquire the data needed for this study. And we compiled over 40,000 arsenic data points for all of Cambodia. And this was part of a much larger data collecting effort as a part of the PAL group, where I think we've collected at least 500,000 arsenic data points and other data for Southeast Asia, but for a lot of other countries around the globe. So we took a subset of that data for Cambodia kind of as our test data set. And much of our initial analysis revolved around Cambodia because these aquifers are less perturbed by groundwater pumping. Therefore, there's a stronger connection between the environmental variables that are measured at the surface and the natural processes that regulate groundwater arsenic in the subsurface. And so we gathered locally integrated measurements of flooding occurrence, which we refer to as duration, and recurrence, which we refer to as frequency, between the periods of 1984 and 2019. These map products were originated from a global surface water data set where we kind of redefined what they were calling water occurrence and water recurrence. And so these flooding values were estimated within a local recharge environment that spans 1.5 kilometers in radius around the entire well. So it's more or less a circular buffer that we mapped out on top of each one of these wells, and then we estimated the flooding frequency and the flooding duration within those recharge environments. And that was important because we wanted to capture the general surface flooding conditions that might result from, say, groundwater and at different depths. And in this analysis, we also neglected any kind of permanent water, and we actually pushed that out of kind of our flooding categories into another category. So we also collected a parsimonious set of other geomorphic variables, including the groundwater well depth, the distance to the nearest river, the width of the nearest river, and the fractional river and lake coverage in these recharge zones. And that's that permanent water category I was referring to. We then evaluated the relationship between these variables, as well as the geochemistry of our flooding regimes. And then we developed a high spatial resolution sub-kilometer, to meter scale predictive model using a machine learning technique called random forest. And we did that to model groundwater arsenic concentrations in Cambodia. So the first result I'm showing you is how well our groundwater arsenic values mapped with respect to our conceptual model. And so we have that same conceptual model here to the left, and then here to the right is a figure that is showing us the median arsenic value that was calculated for each 1% flooding duration and flooding frequency interval. So this is more or less a heat map that has hundreds of little boxes that contain some amount of data. And those boxes are defined by a 1% by 1% interval. And so the colors are showing you what is a median arsenic concentration of the data for each one of these pixels. And since we're using a very large data set, we try to get a little bit creative in how we're visualizing this data. So we thought this was a very nice approach. And what we find is that there's certain combinations of flooding duration and flooding frequency that correlate very well with groundwater arsenic concentration. And that these combinations map quite well against our expected flooding regime and arsenic scenarios. As you can see, in the areas where we see the highest groundwater arsenic are also those that kind of have this moderate to high flooding frequency that we expected to see high arsenic. Likewise, where we see very dry conditions, where the duration of flooding is roughly less than 5%, we see almost unanimously low arsenic as expected. So this was our first line of evidence that demonstrates that flooding behavior is strongly linked to groundwater arsenic contamination and spatial heterogeneity in Cambodia. Now folding in additional information on the relevant geomorphic conditions can help us refine this understanding of the controls and environments that are vulnerable to arsenic contamination. So for instance, we find that at shallower well depths, they tend to have lower groundwater arsenic concentrations across a kind of this wider range of flooding conditions. So what that's suggesting is that shallow wells in this region, which we've marked from 5 to 15 meters, typically have low arsenic regardless of what's kind of the flooding that's going on above them. Likewise, we found that lower groundwater arsenic concentrations occurred when wells were positioned further from a river. Again, irrespective of the flooding behavior of the surface. And that is providing some level of information of if your groundwater well is far enough away from that river geomorphology, such as an active deposition zone that I was referring to in the schematic earlier, then it's potentially much safer from these environmental conditions that would lead to arsenic contamination. And there's many other examples of how these variables interact and how they combine that I can show, but just kind of for brevity, what this is all illustrating is that it's very important to consider relevant and mechanistically tied predictive variables when using, say, like a statistical model, such as a random forest. So now what I'm showing you is what are some of the kind of main patterns in the geochemistry of our flooding defined hydrologic regimes. And so more or less we've characterized the data based on their flooding, their surface flooding behavior. Now we're looking at what is the geochemistry of those samples grouped by their flooding regimes. And we find a nice agreement between flooding and some of the key redox conditions that regulate arsenic mobilization. So this first plot here I'm showing you, and how I've kind of outlined these box plots, they're going from kind of our two anticipated low arsenic categories that were dry, that flood kind of flashy, but then dry thereafter. Then we have our more moderate and high flooding categories, and then kind of our extreme flooding categories. And so we can see that the trends in arsenic, when we kind of group them this way, are kind of how we expected them to be, where we have low arsenic in our dry and flashy floods. And then we have higher arsenic in those that have a longer or moderate duration and frequency. And so some of the key geochemistry variables that are you want to consider are how much dissolved organic carbon is in that groundwater. That would give us some understanding whether there's organic matter that is being degraded, which is again one of those important steps for arsenic mobilization. And we do find that we tend to have higher dissolved organic carbon concentrations in our flooded categories, and typically lower in our other categories. Ammonium is a chemical that also relates to the degradation of organic matter. So for instance, if the organic matter that's being deposited from floods over time is very labile, or it's very easy to consume by microorganisms, that's also going to ramp up the rate of this microbial processing that is important for arsenic mobilization. And so when we find high ammonium, that's a good indicator that there's a lot of organic carbon turnover in this system. And so we also found that our flooding categories had higher ammonium than these other ones. And then the last chemical variable is sulfate, which is indicative of the sulfate reducing conditions or anaerobic conditions that are also needed for arsenic release. And we would expect that areas that are water saturated and are anoxic will have lower sulfate. And then again, that aligns well with our flooding categories here. Okay, so when we use these spatially explicit predictive variables with our random forest model, we found that we can predict groundwater arsenic concentrations from, say, near 0 to over 750 micrograms per liter reasonably well. And I'll walk you through this figure that's summarizing the modeled results in terms of arsenic concentrations. And so what we're looking at are a series of box plots, basically, without the whiskers, where the data, both modeled and observed, they were grouped by several ranges of their respective observed groundwater arsenic concentrations. And those are shown here on the bottom x-axis. And this grouping was done in a way that aligns with the typical ranges of field kit measurements. And that makes up the vast majority of our measured data, our field kits. And those are measured more or less in discrete values. So connecting to the top x-axis, the box plots were placed at the median observed arsenic value for each one of these ranges. And this was done to compare the modeled ranges with an expected error bound that is associated with these field kit measurements, and that error bound being in red. And so to kind of provide a more concrete example, for example, observed arsenic values that fall between 400 and 500 micrograms per liter. The median of that data is approximately 400 micrograms per liter. Then the modeled predictions for this observed range mostly fall between 250 and 500, which overlaps considerably with this expected error bound of observed data. So that would be kind of a group of observed arsenic concentrations that we model quite well in that higher range. Now, to kind of summarize these model results, we've demonstrated that our random forest model can correctly predict precise concentrations of groundwater arsenic within some anticipated error for individual wells and households, roughly 1/3 to half of the time. And so to someone outside maybe of this field, this may not seem all that impressive, but it indeed represents a nice step forward. And that's because we're making predictions of arsenic concentrations for individual wells or households that naturally range orders of magnitude over a very spatially heterogeneous landscape, which is something that very few studies typically do. It's quite rare to see people predicting explicit concentrations. So as I said before, it's often much easier to predict a probability of exceedance than an actual concentration value. And that goes back to the kind of the difficulty of doing this across heterogeneous scales. And then, although I'm not showing, this is not shown, even when we do not correctly predict the arsenic concentrations, we actually still get fairly close, which is important if we're interested in categorizing the risk of exposure, say by safe, dangerous, and very dangerous levels. And so that's kind of what I'm going to show in this next slide. And another way of viewing how well we predict groundwater arsenic concentrations is by comparing the modeled and the observed results by, say, defined ranges. So for instance, here I'm showing you the proportion of groundwater arsenic concentrations that are less than or greater than and equal to 10, 50, and 100 micrograms per liter that were correctly modeled within these respective ranges. So in other words, for all of the measured data that was above 10, what is the percentage of time that we correctly model those data above 10? And overall, we do quite well at predicting groundwater arsenic above or below these thresholds of, say, like safe, dangerous, or very dangerous. Now, an important consideration here is that failing to predict groundwater above these thresholds represents a public health threat in these areas. And what I mean is where we've modeled, what I mean is where we've modeled arsenic concentrations that are in fact below the observed values. However, based on our model results, we don't need to be too concerned with public health threats, given that our model fails to predict above these thresholds, say only 10 to 15% of the time, roughly 5 to 15% of the time. And when this happens, we still generally predict close to these targets. And also coming back to our schematic, now with another mechanism on here, which I'm showing you, which is the floodwaters. So if we're only interested in predicting groundwater arsenic, say above 10, above 50, or above 100 micrograms per liter, we can do so quite well at the individual household scale. Now, the next piece of result that I'd like to show you is that our random forest model performance improves when we take the geometric mean of the modeled arsenic data across a 1 square kilometer grid. And this demonstrates that we can achieve a remarkably close prediction of the average arsenic concentration within only a slightly larger area. And what I'm showing you here is in black and gray are depending on the number of samples that we include in this area. So for instance, the black dots are almost always aligned with our 1-to-1 line here. That's where we have a 1 square kilometer area with greater than 30 data points. If it's between 10 and 30, it still does quite well, but in some cases it deviates by a little bit. And this was certainly one of the more exciting results that we found, because what that suggests is that we can predict the mean arsenic value of, say, a neighborhood very, very well. So if you're someone who is maybe less interested or less concerned about site-specific or well-specific concentrations, but want to get a general sense, what is the average arsenic or concentration that people might be drinking in this neighborhood? Using this approach, we do quite well at predicting that average concentration. And so now the next piece of result I'd like to show you is that our modeling framework can accurately predict the spatial heterogeneity in groundwater arsenic also remarkably well across scales in Cambodia, where we see a near perfect prediction of the variance in arsenic data at separation distances greater than 400 meters. And so the figure what I'm showing you here, this is the variance that is normalized by the P-SIL of a semi-variogram, which is typically an area that it just starts getting flat. And then the separation distances is kind of our scaling metric. And we see that our modeled and our observed roughly at around 400, the patterns and the variances are almost identical. And so this result highlights that our predictive variables are effectively capturing both the fine scale and the entire landscape scale variability in these environmental conditions that regulate groundwater arsenic heterogeneity in Cambodia. Now bringing it back to our schematic, kind of in other words, we're able to effectively predict these sharp gradients in arsenic that are observed over, relatively small scales that might, say, occur on either side of a transition zone and even within a transition zone, as well as very large spatial scales that, say, might occur from next to a river all the way out to Hanoi or something like that. Now, using this approach, we can effectively predict groundwater arsenic concentrations across scales solely using this high resolution, remotely acquired surface parameters with flooding, as well as these other geomorphic variables for anywhere in Cambodia. And that's really one of the advantages of using only remotely acquired data, is it allows us to then kind of extrapolate much more broadly to areas where we don't have or can't collect any field measurements. And what I'm not showing you in this presentation, but certainly would be happy to talk about later on, is we've applied the same approach to southern Vietnam, the Mekong Delta, northern Vietnam at the Red River Delta, and also of all of Bangladesh. And the performance does quite well in all of those regions too. So this is an approach that is can be extended to other areas in Southeast Asia. Okay, and the last couple figures I want to show you is how we can use this these predictions and this method, and then apply it to assess levels of exposure or risk of excessive arsenic consumption. And so I'll walk you through this colorful map. And so here is an example where I used our approach and I modeled the groundwater arsenic concentration for every 100 square meter area. So a very small area for this this region of the lower Mekong of Cambodia, and that resulted in something like 2 million points that encompass this area. I also acquired a high resolution population density data, and that was at the scale of every 1 square kilometer. Now, provided we do a better job at predicting groundwater arsenic concentrations when we upscale our modeled predictions, say to 1 square kilometer, I took the geometric average of all of those individual modeled data points for each one of those 1 square kilometer grids, which is roughly 100 points per area. And so now we have a mean average that is associated with a population density estimate for that area. And upscaling further, we can determine the percentage of the population in each commune or district that is potentially exposed to groundwater arsenic levels between, say, 0 to 10, 10 to 50, and greater than 50 micrograms per liter. And that's this ternary diagram that I'm showing you here on the right. And it's a little bit confusing, I know, with the axes, and that's because the coloring in the data is centered. And so, for instance, the average is roughly 22 on this axis, and then the values are simply, 32, 42, 52, 62 in terms of their percentages, and minus 10, minus 20. And so to provide a more concrete example, this pink area right here, which is defined by this axis over here, and is telling us the percent of population exposed to greater than 50 micrograms per liter arsenic. This bright pink area represents 60 to 90% of that population is exposed to groundwater arsenic greater than or equal to 50. And so when we do this collective scaling and averaging, we see that there's a lot of areas that largely hug next to the Mekong River, where a significant portion of the population could be exposed to groundwater arsenic greater than or equal to 50. And now the image I'm showing you is the population density data for that area. And to the right are the estimates of the percentages and the number of people that could be potentially exposed to these various ranges of groundwater arsenic for this particular region in the figure. Now, provided an entire population doesn't all drink groundwater from tube wells, these numbers more or less represent a maximum number of people exposed or potentially exposed. But even if we assume, say, 30% of the population drink groundwater from these wells, we still estimate that a significant portion of the population is at risk of drinking excessive amounts of arsenic in groundwater for this region of Cambodia. So I'd like to leave you with a few take-home messages, as well as a few points of my future direction with this research. Kind of take-home message number one is that flooding behavior serves as a master variable that integrates the necessary hydrogeochemical conditions that regulate groundwater arsenic levels, that sub-kilometer scale arsenic heterogeneity can be predicted using solely high resolution and remotely acquired surface variables. And then lastly, with improved predictions of groundwater arsenic contamination, they can be used for effective evaluations of household levels of risk or exposure, as well as within communities. So a few future directions. Kind of one of the next steps I'll be taking in this research is applying this mechanistic and this modeling approach to the United States. For instance, in the upper Midwest. This is work that is in collaboration with Mindy Erickson, and I think Mindy is going to be giving a talk for the SRP group coming up. And the upper Midwest is perfect example because a lot of members of our group are kind of doing arsenic-based research up there. But also it turns out it's a very wet environment. There's lots of lakes. And the underlying geology might be most similar to that we see in Southeast Asia. So it kind of provides a nice segue to kind of test our approach and evaluate and more or less apply a lot of the same things we did there, in Southeast Asia to the upper Midwest. One of the next future steps is to begin to fold in additional data on climate, for instance, precipitation, and water use, such as groundwater pumping, to understand the anthropogenic and climate impacts on environmental conditions. And so I think this will lend itself to a really nice complementary forecasting component. In the sense, if we have a really good handle on the climate regimes that are associated with, say, these flooding conditions in Southeast Asia, and these flooding conditions we have data, and the climate data we have for a large time series, we can then begin to kind of find certain patterns and kind of match that with forecasted data for the future and say, well, under this scenario, this is where, climate scenario, this is where we see the flooding conditions that are relevant for arsenic release. And in this area, we're expecting to see climate to kind of turn into that. So particularly excited about that bit too. And kind of the last future direction, which is, for this group, but also as a part of kind of this fellowship program moving forward, is to bring in new expertise from the EHS and epidemiology departments, as well as those at the Columbia Data Science Institute, to begin to kind of bring a lot of this together, work on some of that application, and really start to make an impact. So with that, that kind of concludes my presentation, and I would be happy to take any questions. I'm going to stop sharing my screen. Okay. There's so much chatter going on. Not exactly sure where any of the questions may have started.
Okay. I have a question, Craig. This is Harshad, postdoc from UTSA Geological Sciences. Mm-hmm. Thanks for the great talk. It was really interesting. At one of the points you mentioned that the flooded regions, the groundwaters from those regions showed higher DOC and ammonium concentrations. And So I think the data was suggesting that because of flooding, you have some kind of influx of DOC to the groundwater. Is that okay? So is it on a more like a depositional point of view, like with the flooding, this organic carbon or organic matter is being deposited over the time, which is linked with this arsenic mobility, or it's more like dissolved organic carbon in the flooding water that infiltrates into the ground? So my question is basically, is it flooding that deposits organic matter in the sediments, or is it more a DOC that is infiltrating into the groundwater?
Right. We don't really know which one it is, at least with the data that we have currently. We can't tease that apart. And to kind of summarize, we're asking ourselves, where's the source of this carbon? Is it from the actual river water, or is it from the sediment that's being deposited and then water kind of leaches it and then that DOC goes in? My guess is it could be both. The river water certainly is high in DOC. The sediments certainly can be high in DOC, and through both processes are probably generating DOC that's kind of in the groundwater and then vected further into the aquifer.
Okay, thank you.
I have a question as a very naive epidemiologist. I was thinking, you know, the geographical patterns that we see in Arahazar, Bangladesh. And, you know, you have wells side by side that can be super different in arsenic concentrations. And I was just thinking, but the flooding characteristics cannot be so different. You know, these homes are next to each other. So if one of them is flooded, the other one must be flooded too. So I was thinking, how can this model, how can this variable contribute so much to help you predict? So can you help me a little bit with that?
Yeah, that's right. So we might expect that the flooding conditions would be similar, say, 30 meters from each other, or maybe even 100 meters from each other. But as we get beyond, say, to like 500 to 1 kilometers, then they could be a little bit different. And so that's one answer. The other is we have other variables in there that are, I would say, more precise in terms of scale. So we're getting exact measurements of the distance, which that again, something that's kind of sitting right next to each other. You might expect the same level of arsenic, but you might not if the groundwater is coming from different depths. So that's kind of an example where you might have wells right next to each other that have similar conditions, but if one is very shallow in an area that is potentially more contaminated, one is very, very deep, that could be less contaminated. So that could also kind of cause this small scale variability. It looks like Ben has also a few thoughts on this. Ben, did you want to chime in if you had any?
Yeah, I would to say one thing real quick, and that is, even though the wells are close together, they don't necessarily come from. One of the things to realize about water is it doesn't mix underground very much. So we're modeling with these circles that are reasonably small, but the water is really only coming from one part of that circle. And if we knew better where it came from, the model would be improved significantly. And in fact, that's why even two wells at the same depth can have very different arsenic levels too. If you actually follow the flow path back to where the water came from at the surface, one may be from a dry area and one may be from a wet area, even if the two wells are very close together. So we try to capture that with these hydrologic variables to the best that we can. And Craig has done a really good job figuring out how to do that, but certainly those are both effects there.
I wanted to ask about the temporal variability. How does the model hold, or if there are changes in flooding, how fast would the flooding effect have an impact? Or are you more capturing the chronic average flooding?
So that's a really good question, because the model does not consider really temporal variability, say from year to year. I mean, the underlying data set that was included with this flooding data, it's an integrated kind of evaluation of the frequency and kind of overall duration over the last 35 years. And so in that sense, when we have frequency values that are 50%, that means it would, flood every other year, more or less. But in terms of like coming up with a new model or new predictions that we can feed it like a temporal dynamic, that is currently not something we can do. Although that would be nice.
I have a question, actually. So when you were looking at your modeling, it performed really well for levels above 10 micrograms per liter, but below 10, it wasn't perfect. And so I'm thinking about when you're applying it to the Great Plains or the upper Midwest, do you expect that to be an issue with natural levels might be lower? I guess I don't really know what the levels are in that region.
So absolutely. So if we haven't tried this yet, but if we were to take the same exact model that we essentially assembled from Cambodia and we applied it to the upper Midwest, we probably wouldn't do so great at modeling arsenic for that reason, because the environmental conditions in Cambodia are just different from those in the upper Midwest. But what we can do is take the same exact approach and just repeat it. And so we can more or less fine tune the model and the variables to a new environment. And so presumably, and one thing that we're interested in knowing is if we do that fine tuning process, how well are we able to kind of predict arsenic? So it's a super good question. And for sure, kind of what you highlighted is at least kind of what we've done in Cambodia. We do less well at modeling arsenic less than or equal to 10. And we tend to overestimate arsenic in the low range. But yeah, we'll just have to kind of wait and see whether that's something that also happens when we apply it to the upper Midwest.
I had sort of a naive question. Are you going to have to think about how the flooding occurs differently when you think about what's happening in the sort of northern plains, Great Plains, upper Midwest, where flooding happens when you get snowmelt? So you've had all the snow accumulate over time, and then it sort of all melts at once and dumps into, I don't know, the aquifers, the rivers, everywhere. Versus in Cambodia, where I assume it's more of a monsoon instantaneous like thing. So does that add a variable that you might have to think about?
Certainly. So like if we begin to look, well, I guess I'll say two things. We have the ability to not just describe flooding behavior, but any kind of surface water. So for instance, in the Great Plains, there's tons of lakes. And we may find that we see a pattern in the relationship between surface water and arsenic, and we might relate that more to lake recharge that is permanent, and it may not be associated with a seasonal effect. That said, if we see values that might reflect a seasonality component to it, then we would kind of go down that road and maybe think about more, is this a tie to, say, the spring snow melt time period? So certainly, as we begin to apply, we begin to see new results, we're going to have to perhaps think differently about what these environmental conditions actually are. So it's, and they may not be exactly, at least from the kind of water perspective, it may not be exactly the same, I guess, method that we see in Cambodia, but it could still result in a similar degree of like effect on arsenic contamination. And that's kind of, again, highlights the importance and the role of surface water in general.
Any other question that you might have? It's your opportunity. These are our last few minutes.
So I don't have a question, but I do want to offer praise to Craig for the clarity of the presentation. You brought us all along, even the non-geo people, and I really appreciate it.
Yeah, thank you very much.
So I had a quick question. Craig, this is Sugata from UTSA. I was wondering that, have you thought about, and especially in the South Asia or Southeast Asia, the duration of the monsoonal months and the amount of the flooding that is pretty much happening throughout the monsoon? Do you think that the duration or the time of these events has any bearing on the effect of arsenic being high in some of these wells that we see mostly in the shallow wells, 5 to 15 meters that you mentioned?
So, like for instance, if the flooding occurred at a time that the period was warmer,
Right.
that might be an instance where if the temperatures are warmer, the flooding is occurring, there might be more active microbial processing of that organic matter or the kind of the geochemical conditions that lead to the dissolution of arsenic. I'm not really sure the answer to that, because I guess I haven't thought too much about how important the timing of the flooding is, because I know that if flooding occurs, the timing occurs differently across Southeast Asia. That certainly would be an excellent thing to think about. And as we begin to go maybe delve more into comparing these different regions in Southeast Asia, if we begin to see unusual differences in the relationship between flooding and arsenic, that would certainly be an excellent thought to go down.
Sure.
But yeah, I guess I can't, at least off the top of my head, I can't
Sure.
offer any explanation.
Fair enough. Thanks.
Yeah.
There is a question from Maya. She was asking if you are planning on extending this model to other areas beyond the Midwest.
Certainly, yeah. We're just kind of going to start in the Midwest because it's there's lots of collaborative linkages there, and we've already acquired a very nice data set for that region. But this certainly can be applied to other areas in the U.S. And that's kind of the luxury, but also kind of one of the goals that we had in mind in using remotely acquired data that can be accessed almost anywhere on Earth, is that it's very accessible. And hopefully one of the things that, well, not hopefully, this is something that's going to make its way into the paper, is kind of a very step-by-step outline and a lot of the code that can be reproduced and applied elsewhere. So even, we'll certainly focus on the upper Midwest and maybe some other areas such as around the Mississippi Delta, but we're going to make it available for others to also kind of try it out too.
Wonderful. So we are 1 minute to go. So if there are no more questions, I just want to say thank you and congratulations, Craig, for your outstanding presentation. Thank you also, Arthur, for your fantastic presentation too. And thank you to all of you for coming to these interdisciplinary events. I think it's amazing when who speak different languages come together. I think we all become smarter by the end, at least a tiny bit.
Little by little.
Little by little, day by day, month by month. So please stay tuned and come back next month for our Columbia University Superfund Research Program seminar. Thank you, everybody. Have a great evening.
Thank you, Anna.